Right, okay. Students, can you all hear me? Can you hear me? Right. Right, okay. So, students, good evening for all of you. So, today we are going to conduct the session number 8 of organic reaction practice. So, can you remember the last week, the last session, we were discussing about the aldol condensation. So, therefore, let's quickly revise aldol condensation reactions and then let's go for the next reaction. Okay. Now, we know that aldol condensation or else self-condensation reactions of aldehydes and ketones. When we add aqueous sodium hydroxide, it's connecting to the same molecule. So I told you how to get the products easily for these kind of reactions. So let me consider the ethanol molecule that we discussed. So this is the example that I discussed with you when we discussing about the reaction mechanism. So therefore, let's go for the ethanol molecule. So in the ethanol molecule, you can see the students, the first thing we have to do is CH3. And I'm going to take this carbon hydrogen bond down. And this is converted into OH, right? And we know that this is the alpha carbon. We have to remove alpha hydrogen from alpha carbon and then connect that alpha carbon to this carbon atom, then CH2, C double bond OH. So this is considered as actually a aldol product because aldehyde group and the alcohol group is there. So therefore, this is considered as aldol product. Go for the next one, second one. So here also what we have to do, CH3, CH3. And here we can put the carbon hydrogen bond down. Carbonyl group converted into OH. And this is the alpha carbon. We can remove alpha hydrogen from alpha carbon. Then it is converted into CH3, CH3, C double bond OH. This is the product of the reaction. So when you go for the third one, so third one is a ketone, right? So you can choose any of the carbon atoms here as the alpha carbon, doesn't matter, right? Already you can choose any carbon atom. So let me take the left hand side one. Then I can say that CH3, OH. So we have to put this bond down, CH3. After removal of alpha hydrogen from this compound, this is CH2, C double bond of CH3 in this way, right? And here you can see that sodium hydroxide is added for this compound. What will happen? So here we have two alpha carbon atoms, right? So you can take this one or either this one, doesn't matter, right? So that means we have two products. Right? If I consider left hand side one, left hand side carbon atom, after removal of one hydrogen there, CH3 OH, CH2 CH3, CH2 C double mondo CH2 CH2. So this is one of the products that we can obtain. Remember that we have another product. So what is the next product? So we can say that if this carbon atom, right side carbon atom is the alpha carbon atom, I can remove one hydrogen from there and then I can connect the relevant carbon atom for this compound. Then the answer should be like this. So I can consider that CH, CH3, C double bond to CH3. Right? So likewise, we can obtain two products for this reaction. product number 1, and this is the product in this. Okay. Right. So this is the aldol self-condensation reactions, how to obtain the main product. Okay. Raise your hand those who understood the aldol condensation, the self-condensation reactions and its reaction mechanism that we discussed. Raise your hand quickly. If you have any doubts, let me know. Good, right. Okay, now students, we know that after this actually we have another step, right? Can you remember? Number 5. So when we add H plus and heat in this way, now you should be able to obtain the product directly. CH3, C double bond OH. We are adding aqueous sodium hydroxide at first, and secondly H plus, right? So what will happen here? First of all, we know that according to the condensation reaction, CH3, COH, H and CH2, C double bond O, CH3 is produced. And then H plus and heat, this is actually dehydration, right? So after addition of H plus and heat, the dehydration reaction will take place. That means this OH group is eliminating with the one of the hydrogen atoms. So then according to the Zaitsev rule, we know that always hydrogen should eliminate from the carbon atom where poor number of hydrogens are connected. So therefore, this is the carbon atom where poor number of hydrogens are connected. Then one hydrogen removed from here, OH removed here. Then you can see that this is carbon-carbon double. Remember students, this is actually considered as alpha beta unsaturated what? Aldehyde or ketone. This is a ketone. Okay. Alpha beta unsaturated ketone. Okay. Can you understand? This one should be H, right? Because we have used ethanol, alpha beta unsaturated aldehyde. Okay. Can you understand? Do you have any doubts there? Number 5 should be like this. Right. So let me do the same thing for the ketone. Now you should be able to get the product directly. Yeah? Number 6. CH3, C double bond O, CH3. And I'm going to add here sodium hydroxide and then H plus heat. And then what will happen? CH3, OH, CH3, and CH2, C double bond O, CH2 in this. Right? But after addition of H plus and heat, what will happen? Dehydration will take place. OH is eliminating with the hydrogen, which is connected to poor number of hydrogens and carbon-carbon double bond. So this is alpha beta unsaturated ketone, not an aldehyde because C double bond is CH2. Okay. Number 7. Just imagine we have CH3, C double bond and phenyl ring, a ketone which is containing phenyl ring. I'm going to add sodium hydroxide aqueous, secondly H2O plus N. Right. First of all, you can obtain the product, the first product, CH3, OH, phenyl ring, and CH2, C double bond O, CS, phenyl ring. So after addition of H plus and heat, OH eliminating with the hydrogen here, then it's making carbon-carbon double. Okay. Number 7. Number 8. CH3C double bond OH plus CH3C double bond CH3 acetone. Right? That means we have ethanol and acetone both added together, and then sodium hydroxide aqueous is added. Secondly, H plus and heat. So what are the products? So first of all, let me connect this molecule to this one. So therefore CH3, right? CH3, COH, hydrogen here. So I can choose the alpha carbon atom from the second compound. Can you understand? So now here, not the same molecule. The second molecule is connecting as the nucleophile. So therefore, after removal of alpha hydrogen here, then the remaining things are CH2, C double bond CH2. So this kind of a product is possible. Students, remember the vice versa also can happen. That means we can exchange them. Let me consider the first molecule as this CH3, COH and CH3 group here. And this is the alpha carbon, hydrogen is removed from there. Then CH2, C double bond OH in this way. Then both the products are possible, right? So if I consider this is number 1 and number 2, so this is the product that we obtain by connecting number 1 and number 2 in order. And this is the product that we obtain by connecting number 2 and number. Got it? Right. That's all. So that's all about the aldol condensation, right? Students, do you have any doubts, anything that you want to ask from me regarding the aldol condensation? Raise your hand, those who understood the aldol condensation clearly. Quickly raise your hand. Good. Right. Then let's move to the next reaction. So we are going to discuss special conversion reaction number 11. So write on the topic, special conversion reaction number 11. Special conversion reactions number 11. Halogenation of benzene. Halogenation of benzene. Special conversion reactions number 11. Halogenation of benzene. Quickly. Students, we have discussed this one under the theories also. Can you remember? We have a benzene ring. So we can add a catalyst, Lewis catalyst along with this. Now if we are using chlorine or bromine, chlorine along with anhydrous, a Lewis catalyst like FeCl3, ferric chloride. Then what will happen? Instead of that hydrogen, now chlorine is coming to the compound. As you can see here, very easy. Now instead of this hydrogen, now chlorine came to the compound. Right? So that's so. As a byproduct, we can say that HCl is the byproduct. So we can do the same reaction with Br2 also. We have the benzene ring, and I'm going to add here Br2, a Lewis catalyst like again FeBr3. That's also possible. So can we put here aluminum trichloride, aluminum tribromide? Yes, any Lewis catalyst. Any Lewis catalyst. So if I use FeCl3 here and FeBr3 here, yeah, that's fine. It's okay, right? Because the main compound that is adding to the compound is benzene ring is Br. So the catalyst that you are adding is that one should be a Lewis catalyst. That's all, right? It's not compulsory to have the same element in the catalyst. No, that kind of rule. No? So what will happen instead of hydrogen, bromine is coming there. So the byproduct is HBr. So as you can see here, instead of hydrogen, now bromine came to the picture, right? Remember, we can't do the same reaction in the presence of iodine, right? Unfortunately, we can't add iodine for this molecule, benzene, directly. Actually, we have a different method for that one. So we can't do that. Iodine anhydrous ferric iodide. Will there be any reaction? No. There is no such reaction. We can't connect iodine for the benzene ring direct. Only chlorine and bromine. Okay. Halogenation of benzene. Right. We can produce chlorobenzene and bromobenzene in the presence of anhydrous Lewis catalyst. Okay. Quickly copy down this one. Done. Eh? Now let's go for some exercises. So today we have to cover some reactions. We have to finish this one quickly. Okay. Within this month, anyhow we have to complete organic chemistry. So let's say. Okay, are we done with this one? Shall we move to the exercise? Yeah. Right, okay. Now, exercise, question number 1. So you can revise the all reactions that we learned by doing these conversions. So therefore, quickly do these things. Ethyl chloride converted into ethanol, then converted into ethanol, then it is converted into an aldol product like this. Then you know what we have to do. What is the region we have to add there? Then they have added H plus and heated. I think I gave you the answer, right? Then here, after adding a compound, we are having a dibromo compound along with the aldehyde. You know what we have to add simply. So for this one, we are adding some compound and producing carbon-carbon triple bond at the middle of the compound in this way. After adding a region, number 1. Number 2, we have benzene going for chlorobenzene, producing Grignard region from there. Then intermediate product after adding an aldehyde. After that, we are having this kind of a alcohol. We can produce benzoic acid after addition of a reagent. Benzoyl chloride is produced. And an amide like this is produced. Sorry. Let me quickly go with the first one. Aqueous potassium hydroxide or else aqueous sodium hydroxide. Then we know that this is a primary alcohol. In order to stop where an aldehyde case, we have to add PCC, right? Right. Remember, we can't add acidic KMnO4 because when we add acidic KMnO4, that will go for a carboxylic acid. So therefore, keep that in your mind. Definitely, you have to add their PCC. Right. So this is the reaction that we discussed last week. Self-condensation, aqueous sodium hydroxide should be added. So thereafter, we know that H plus and heated. Then two bromine atoms are connected, which means Br2 is added. Bromines are eliminated with the hydrogens, definitely. Alcoholic KOH is added to the compound, right? Dehydrobromination. So in here, we can put that HCN, right? HCN, aldehyde ketone is reacting with HCN. Number two. So just now we discussed that one, chlorine reacting with anhydrous ferric chloride. Magnesium diether to produce Grignard. And what is the aldehyde they have added? Only with one carbon, that means for sure that is methanol. Then hydrolysis. Look at this one, primary alcohol converted into a carboxylic acid. So therefore, so let me use here potassium permanganate in the acidic medium. Then PCl5 here. And here you can see that chlorine converted into this one. So that means they have added primary amine like this. Ethylamine is it? The second one. Quickly come with this, please. Done, eh? Right. Then I'll go for the third one. Number three. So we have a secondary alcohol like this. I'm going to consider sulfuric and heat. Dehydration reaction, right? Then HBr is added in peroxide medium. After that, aqueous KOH is added. Aqueous KOH. Then PCC is added. After that, aqueous sodium hydroxide is added. H plus and heat. Then Grignard region. CH3 MgBr is added. Finally, hydrolysis. complete the reaction. Let's move to the fourth one. We have benzene ring. I'm going to add Br2 anhydrous ferric bromide, FeBr3. Magnesium triether is added. An aldehyde is added. H3O plus is added. Acidic KMnO4. Number 1, sodium hydroxide, and then H plus heat. The product is obtained. For that product, we are adding Br2. And finally, KCN is added. Give me a minute. Right, okay, quickly complete the third one and the fourth one, quickly. So what about the third one? So we have added considered sulfuric and then heated. Dehydration. So therefore, OH is eliminating with the neighboring carbon atoms hydrogen. So we can choose any carbon atom because that is a symmetrical compound. So therefore, CH3, CH double bond CH2. Then HBr added in the peroxide medium. Then what will happen? We can say that CH3. We know that when we add HBr according to the Markovnikov rule, hydrogen should be added to the carbon atom where carbon is rich with hydrogen. But this is actually peroxide. After adding peroxide, we know that anti-Markovnikov rule. We have to go with the anti-Markovnikov rule. So therefore, hydrogen should be added to the carbon atom where poor number of hydrogens are contained. So therefore CH2, and here we have CH2. Then potassium hydroxide aqueous, that means CH3, CH2, CH2, OH. So PCC is added for a primary alcohol. So then we can say that CH3, CH2, C double bond OH. Then sodium hydroxide aqueous is added. Then we can say that CH3, CH2, COH, H here, and H, CH3, C double bond. After addition of H plus and heat, then C2H5, this way. Then Grignard region is added. No effect for the double bond, it is remaining as it is. OMG-Br is produced here, HCH. But finally you can have this kind of a product. Okay. What about the fourth one? Bromobenzene is produced. After that, Grignard region MgBr is produced. So thereafter, we can say that CH3 OMgBr H phenyl ring. So after addition of H3O plus CH3 OH H and the benzene ring here. Acidic KMNO4 is added, so therefore CH3 then sodium hydroxide H plus feed, so therefore we can say that aldol condensation product should be like this. First of all, write down the product, aldol product. But remember, they have secondly heated this one with H pluses. Then we know that dehydration will take place there. OH is eliminating with hydrogen. Carbon-carbon double bond. Then Br2 is added here. Phenyl ring. Okay. KCN, right? KCN means bromine is reacting with this one. Two cyanide groups are coming in this way. Right. So this is the third one and the fourth. Shall I erase third one? Are we done with the third one? Okay, now students, I'm going to give you a conversion. You have to do this one within maximum 6 steps. Okay, try this one. Number 5. We have a compound like this. C double bond OH. Not more than in 6 steps. Maximum number of steps are 6. Give it a try. You can do it. Try this one. Right, okay. Anyone completed this conversion? Anyone? Not yet. Maximum 6 steps. Right, okay. I'm going to do this one. Look at this one very carefully. Yeah? Now, students, as you can see here, you can decide what is the last step. Why? Two bromine atoms are connected. So therefore, definitely this one should be a double bond. C double bond OH. And Br2 is added. Okay. And even you can decide the next, the previous step also. Why? Aldol condensation. And then second step is H plus and heat. Yes. I can say that the compound that they have used is CH3CH2 C double bond H. What do you say in this? So that means this is the aldehyde they have used, propanol. Okay, propanol. Then now here I can say that I'm going to add alcoholic KOH. Right. And then I can say that HBr, HBr in the peroxide medium. That means anti-Markovnikov CH3, CH2, CH2Br. Then I have this kind of alcohol. Yeah, I can go this one. Go through aqueous KOH and then PCC. 1, 2, 3, 4, 5, 6. 6 steps are there. Okay, alcoholic KOH is added, alkene is produced, HBr in the peroxide medium, Anti-Markovnikov rule. Alcoholic KOH, Br can be converted into OH. Primary alcohol oxidized into aldehyde by adding PCC. Self-condensation reaction and addition of Br. That's all. 1, 2, 3, 4, 5, 6. Okay. Right. So that's all about the next one. We discussed that halogenation of benzene, right? Okay. Now students, let's do some conversions related to the aromatic capability. That means directing abilities, right? Can you remember under the benzene we learned in theories, orthopara directing groups, meta directing groups. Orthopara directing groups and meta directing groups actually affecting to the organic conversions as well. Because we know that if there is a monosubstituted benzene ring, the second group which is coming to connect for the benzene ring, right, is decided by that the first group in the benzene ring, right? So then we have to decide that group is orthopara directing group or meta directing group. So I told you before what does mean by orthopara directing, orthopara positions and the meta positions, right? Now when you consider, I'll revise that one quickly. If I consider the benzene ring in this way, now this is monosubstituted benzene. Remember, students, monosubstituted means one group is already connected, right? If something is not there, we can say the hydrogen is there, right? So therefore, monosubstituted benzene, a group is connected there. So relative to this monosubstituted group, relative to this group, we can give the names for the benzene. Actually, we have remaining 5 positions after connecting this X atom, X group. I can name this one as number 1. Then the remaining positions are 2, 3, 4, 5, and 6. And remember, students, these 2 and 6 positions, they are known as ortho positions of the benzene ring. 3 and 5 positions, they are known as meta positions of the benzene ring. And here we can see that number 4, what is it? This is considered as para position. Okay, right? So likewise, we have ortho positions 2 and 6, para position number 4, and meta positions 3 and 5, right? So now we have to decide whether this capital X group is directing the second group to the benzene ring, right? To which place that first group is directing the second, whether it is ortho position, meta position, or para position. So that is known as what? Aromatic directing ability, right? So therefore, write down the compounds. Directing ability of aromatic compounds. Right? Directing ability of aromatic compounds. So in the theories we discuss, we had enough discussion of directing abilities, but in order to do the conversions, again, I'm going to revise a small part of this, small theory part of this one. Then we can go for the questions. I'm not going to discuss this one in detail because in the theories we already discussed that one. Directing ability of aromatic compounds. Right. Now, remember students, now we have 3 type of questions, right? Ortho, meta, and para. We categorize actually these compounds as ortho-para directing groups and meta directing groups, right? Ortho-para directing groups and meta directing groups, right? So draw the benzene ring quickly again in this way. X. And as we discuss, we can give the numbers for the benzene ring as 1, 2, 3, 4, 5, 6. Or else you can start from, you can go for counterclockwise as well. 1, 2, 3, 4, 5, 6. Doesn't matter. Right? Whatever the method, it doesn't matter. So you can see that 2 and 6 coming for ortho. Ortho. 3 and 5 positions are meta. And 4 is para position. So our first topic is ortho-para directing groups. Actually, we are discussing ortho and para positions together. Right? I'll tell you the reason behind that one. So our subtopic is ortho-para directing groups. Ortho-para directing groups, or else we can say that 2, 4 directing groups. Right? 2, 4 directing groups. Right? Remember, students, what are these ortho-para directing groups? Exactly. What does mean by this ortho-para directing? Remember, ortho-para directing group means actually they are giving electrons for the benzene ring. Now just imagine capital X, right? If capital X is a ortho-para directing group, we can say that it is giving electrons for the benzene, right? So that means they are electron repulsive groups, right? They are giving electrons for the benzene ring. Since they are giving electrons for the benzene ring, what will happen is the ortho and the para positions are becoming negatively charged, right? They are giving electrons, right? If X is a ortho-para directing group, it can give the electrons for the benzene ring. So it is activating the ortho and para positions of the benzene ring. Activating means they are giving the negative charges for this ortho and para positions. I'll discuss that one. I'll explain that one using the resonance of the compounds. Right? When we consider ortho-para directing groups like OH, NH2, phenol, and aniline, we can explain that one. By the resonance, we can explain how that ortho-para positions are activated. Can you remember what is the characteristic reaction type of benzene that we learned? What is the characteristic reaction type of benzene? What is it? Yes, SC reactions. SC reactions means we can say that electrophilic substitution reactions. Electrophilic substitution reactions are the characteristic reaction type of benzene. That means, students, electrophiles are coming towards the benzene ring. We know that electrophiles are the positively charged species. They are deficient with electrons. They need electrons. They are looking for electrons. If they are looking for electrons, they have to go for the places where the electrons are rich. So you can see that the ortho and para portions of the benzene ring, now they are rich with electrons. Electron saturated areas. Then electrophiles are easily connecting there. Can you understand? That's why these groups are known as ortho-para directing groups. That means the second group which is looking for to connect, which is looking to connect for the benzene ring, should be connected for these ortho and para positions. If the first group that connected the benzene ring is a ortho-para directing, otherwise it cannot happen. Right? So therefore, keep that in your mind. If capital X is an ortho-para directing group, it's giving electrons to the benzene ring, by activating by activating ortho and para positions. Ortho and para positions. They are known as, write with me quickly, they are known as electron repulsive groups. They are known as electron repulsive groups. Therefore, electrophiles can easily connect to the ortho and para positions. Ortho and para positions in the benzene ring. The benzene ring. Okay. Students, how we can identify orthopara directing groups? What is the method that I taught you? How we can identify orthopara directing groups? What is the method? Can you remember? Yes, no double bonds for the group that is connected to the carbon atom in the benzene ring direct. Okay, so we can easily identify orthopara directing groups by not having double bonds or triple bonds for the atom which is directly connected to the benzene group. Right? Keep that in your mind. We can easily identify orthopara directing groups by not having double bonds or triple bonds for the atom which is directly connected to the benzene ring. If there is a double bond or triple bond, remember, it's going for the meta directing. Right? We can categorize that one under the meta directing. Right? So I'll give you some examples for the orthopara directing groups. So are we done with these things? Shall I erase these? Right. Now examples for orthopara directing groups. What are the examples? I told you that there should not be any double bonds or triple bonds for the atom which is connected to the benzene ring directly. Now look at this one. Toluene, methylbenzene. Are there any double bonds or triple bonds for the atom which is connected to the benzene ring? Atom connected to the benzene ring is carbon. No double bonds, triple bonds. So therefore, this is orthopara directing group. And what about this one? NH2. Yeah, nitrogen doesn't have any double bonds or triple bond. Therefore, that is orthopara directing group. Look at this OCH3. Are there any double bonds or triple bonds? No. Orthopara directing. Number 4. NH, C double bond or CH2. Nitrogen is the atom which is connected to the benzene ring directly. So that nitrogen atom doesn't have any double bonds or triple bonds. But remember, the next carbon atom is having a double bond. So that's a different case. Right? I told you that the atom which is directly connected to the benzene ring should not have any double bonds or triple bonds. Right? Number 5. Ethyl benzene. Yeah, perfectly all right. Number 6. Chlorobenzene. Fine. No double bonds. So these are few examples for the orthopara directing groups. Right, okay, done. Now, students, let's explain the orthopara directing ability using the resonance. Write down a bullet point like this. Orthopara directing ability can be explained by resonance of compounds. By the resonance of compounds, right? First of all, let me take here chlorobenzene. Right? Let's see how that orthopara directing ability come to the chlorobenzene like compound. How it can show the orthopara directing ability. Let's see. Students, now look at this one very carefully. Listen to this one very carefully. We know that chlorobenzene is a compound like this. It's having a 3 lone pairs, right? Now we know that orthopara directing group means the one who giving electrons for the benzene ring. Electron repulsive groups, right? Electron repulsive means they tell that we don't need electrons. I don't need electrons. You take. So likewise, it's giving electrons for the benzene ring, right? In this giving. Then we know that if it is giving electrons for the benzene ring in this way, this double bond, right? So this double bond, now these electrons are giving for the benzene ring in this way. Then carbon cannot have, now here already 4 bonds are there. After making a double bond between this carbon chlorine, carbon cannot have 5 bonds. So therefore this bond has to be broken. Then we can see that here we have a product like this. Right, chlorine is positively charged. Students, can you see that ortho position, one of the ortho positions in the benzene ring, now it is activated negatively. Therefore, electrophiles can come to this position and can be easily connected to there. Can you understand? Right? Then the next thing, this lone pair, electron given for this one, and this bond is breaking to here. Right? Then we can see that negatively charged here, and chlorine is positively charged. Can you see that the only para position in the benzene ring is activated negatively? Then why can't electrophiles can come and connect to here? Can see that, right? Para position has been activated. Now these 2 electrons are given for this carbon-carbon double bond, and this bond is breaking down. Then we will have a product like this. Right, you can see that the next ortho position has been activated negatively. So therefore, you can see that negatively activated means electrophiles can be connected easily for this place. At next, what will happen? These 2 electrons are given for this carbon-carbon bond. And then carbon cannot have 5 bonds. Again, this carbon-chlorine double bond has to be broken. Then we can see that finally, we are having a compound like this. Here it is. Right? So as you can clearly see that ortho and para positions of the chlorobenzene have been activated, right? Negative ortho position, negative ortho position, negative para position. So therefore, electrophiles are easily come to this compound and connecting here. That's why these are known as ortho para directing groups. Likewise, I'm going to consider another example, aniline, NH2. Example number 2. Look at this one. Here it is aniline, NH2. So there is a lone pair, right? So what will happen as we discuss? These are orthopara-dating groups. They are giving electrons for the benzene ring, electron repulsive groups. So this lone pair is given for this carbon-nitrogen bond. Then carbon cannot have 5 bonds, so therefore this bond has to be broken. Then we can see that here you see that the ortho portion of the compound is activated. Right? Now these 2 electrons are given for this bond. This double bond has to be broken. Then the para portion is activated by taking electrons in this way. Para portion is activated. Nitrogen is positively charged. Right? What will happen next? These 2 electrons are given for this carbon-carbon double bond. Now this double bond has to be broken because carbon cannot have 5 bonds. Then you can see that the remaining ortho portion again activated negatively. Can you understand? Then again, these 2 electrons are given for this carbon-carbon double bond. And this lone pair is given for nitrogen again. Then it is producing. So this is actually considered as ortho para, right? Ortho and para portions are activated, right? So likewise, we can take any kind of an example and explain like this. Okay. Right. So quickly complete this one. Put the arrows correctly. Huh? Are we done? Shall we move to the next type? Meta-directing ability. Raise your hand those who understood the ortho-para-directing ability quickly. Do you have any doubts here? Actually, we have already discussed this one. Right. Then let's quickly move to the meta-directing ability. So the second type is meta-directing ability, or else we can say that 3 directing ability. Okay. Plus, orthopara-directing groups are electron repulsive groups. They are giving electrons for the benzene ring. Then tell me, what will happen in the case of meta-directing groups? Meta-directing groups are taking electrons away from the benzene, right? If capital Y is a meta-directing group, I can say that it's taking electrons from the benzene, right? One is giving, the other one is taking electrons. Can you understand? So therefore, what will happen here, as you think? By taking electrons, what is the effect that will happen to the benzene ring? We know that if someone is losing electrons, that one should be positively charged. Yes. So I told you that ortho and para portions are becoming positively charged. So then benzene cannot do electrophilic substitution. No. Still benzene can do electrophilic substitution. How? Remember, even though that ortho para portions are positively charged, what do you think about the meta portions? Huh? What do you think about the meta portions? Meta portions are relatively negative charge. Relative to the ortho para portions, it is negative charge. We don't have negative charges on the benzene ring in the meta portions. But remember, sorry. But remember, relative to the ortho and para portions in the benzene ring, now these meta portions are what? Negatively charged, right? Then we can say that electrophiles are easily connecting to the meta portions of the benzene ring, not for the ortho para portions, because electrophiles are positively charged. They cannot connect for again positively charged areas, right? Electrophiles are looking for the places where the electrons are rich. Now in the benzene ring, ortho and para portions are electron poor areas. Then can electrophiles connect there? Then electrophiles will connect for the relatively negative charge. There is a small negative charge compared to the ortho and para portions. Then they are connected to the meta portions, right? Then write down this way. If capital Y is a meta-directing group, it is pulling electrons from the benzene ring, by deactivating ortho and benzene ring, ortho and para portions are becoming positively charged. Positively charged and meta position relatively negative charge. They are acting as electron attractive groups. Therefore, electrophiles are connecting to the meta position of the benzene ring. Quickly complete this one. Students, I told you that orthopara directing groups can be identified by not having double bonds or triple bonds in the atom which is directly connected to the benzene ring. Then tell me now how we can identify meta directing groups. Meta directing groups can be identified by considering the double bonds and triple bonds, right? By double bonds and triple bonds in the atom which is directly connected to the benzene ring. Can you understand? So this is a good chance to revise the theory part that you learned. If you have any doubts, tell me. Quickly complete this one. Asma, these days you are fasting, no? Do you have school these days? Oh, holiday. Holiday, right? Have school. It's very difficult, no? Not that difficult. So, like you people, actually, I can't stay like that. It's very hard. Fasting, no way. Example for the meta directing groups. Look at this one. C double bond OH. An atom is having a double bond. Carbon is having a double bond. C double bond or CH3. Meta directing group. Benzoic acid. Yeah, of course. Meta directing group. cyanobenzene, carbon triple bond, nitrobenzene, NO2, if there is a double bond in the atom which is directly connected to the benzene ring, definitely it should be a meta-directing group. So the meta-directing ability also can be explained by the resonance, right? With me quickly. We have already discussed this one, so quickly write down. Meta-directing ability can also be explained by using resonance. For an example, let me consider benzaldehyde. Right? Now look at this one. Yes, we have benzaldehyde compound. Now, meta-directing ability means, students, we know that they are taking electrons from the benzene ring, right? They are pulling electrons from the benzene ring. So therefore, what will happen? Oxygen is taking electrons from the bond. Then carbon has to satisfy the octet after breaking the double bond. Then what carbon will do is, carbon is breaking the double bond in this benzene ring and satisfying the octet and taking electrons from the benzene ring. Can you understand what happened? Oxygen is taking electrons from the double bond because it is a meta-directing group. In order to satisfy the octet of the carbon atom has to take the electrons from the benzene ring. Therefore, this carbon-carbon double bond in the benzene ring is breaking. Then we have a product like this. This is positively charged now. Double bond here. Now here oxygen is negatively charged. Got it? Right. Now what will happen? In order to complete the electron deficiency in this carbon atom, what will happen is this carbon double bond is giving electrons for these two carbon atoms by breaking that bond. What will happen is in the para position, you can see electron deficiency. Right? Now the electron deficiency in the ortho position is complete. But now in the para position, there is an electron deficiency. Now you can see that ortho position and the para positions are positively charged. So therefore, electrophiles cannot come to these ortho and para positions. No way. They will repel. Okay. Then, in order to complete the electron deficiency in this para position, what will happen? This bond is breaking and giving electrons for these two carbon atoms. Right. Then you can see that the next ortho position is positively charged. The next ortho position is positively charged. Right. Now again, in order to complete the electron deficiency in here, this bond is breaking and giving electrons to here. Then again, carbon has to satisfy the octet, taking the electrons from the oxygen atom and making oxygen double bond. Right? Breaking, making. That's what will happen in the resonance, right? In this. As you can see here, both of positions and the para position is positively charged. electrophiles should be connected to the meta-positions, at least to the meta-positions, because meta-positions are relatively negative compared to the ortho and para-positions. I'm using the term relatively negative because I can't say that meta-positions are exactly negative. I'm taking another example, nitrobenzene. I'm taking another example, nitrobenzene. Right. So let's draw the resonance of nitrobenzene. Same thing as benzaldehyde. Remember, students, oxygen is pulling electrons. Then nitrogen has to satisfy the octet here. Now nitrogen is positively charged here already. This positively charged. So therefore, nitrogen has to satisfy the octet. Therefore, what will happen? This carbon bond is breaking and giving electrons for the nitrogen. Then we can see that a product is obtained like this. This double bond has been broken, therefore positively charged. Now nitrogen is making a double bond here. Two oxygens are there. Both the oxygen atoms are negatively charged. Both the oxygen atoms are negatively charged. Nitrogen is positively charged here in this way. Now what will happen? Same thing repeating. In order to satisfy the electron deficiency, in order to fill that deficiency, this bond is breaking and giving electrons for this bond. Then we can see that a product is obtained. Then you can see that in the para position, there is an electron deficiency. Then again, in order to fill the electron deficiency here, this bond is breaking. What is the next step? Now, this electron is giving for this bond, and oxygen is giving electrons for the hydrogen atom in this way, making double bond like this. In this compound also, you can see that ortho and the para positions are positively charged. Benzene ring is deactivated by giving positive charges for the ortho para positions. Therefore, the meta positions are relatively negative charge. Electrophiles are connecting for the relatively negative charge meta positions. That's why they are known as meta directing groups, right? I taught you this one for the second time, right? In the theory class, we discuss again. Again, now we discuss this one under the reaction sessions, okay? Now you should be able to draw these things correctly with the correct arrows. You have to show the arrows in the exam. Don't use the red color pen in the exam, but you can show this one in this way, right? So is it compulsory to put the arrows? Because in the past paper book, sometimes they haven't mentioned the arrows. They just write down the compounds. Better you mention the arrows, right? Because let's show them that we know how to get the resonance in this. It's not a big deal, right? Amaru Megan. Yes. Quickly complete this one. Let's go for the next conversions. Okay, students, are we done? Do you have any doubts here? Raise your hand, those who understood the ortho, para, and meta directing ability quickly. So when do you have the next kinetic session? Students, I couldn't conduct the kinetic session. I couldn't conduct last week paper session also. So I can remember both of them. I'm going to conduct both the two sessions on the OA day, next Wednesday. OA is next Wednesday, right? Am I right? 13th. Morning and afternoon, I'm going to conduct the miss sessions, okay? Anyhow, the plan is like this. in this month, chemical kinetics and organic chemistry will be over, right? I put some extra sessions and everything, and anyhow, right? I also don't know. I haven't planned yet, but I'm going to finish that. That is my target. Let's see what will happen. Right. Okay. Students, raise your hand. Those who understood the orthopara and metadirecting ability quickly. Okay. If you have any doubts, put your doubts in the chat box. Huh? So let's get a small summary like this. meta directing and deactivating groups. Therefore, they have less tendency to do the electrophilic substitution reactions. Okay. These halogens actually can categorize like this. They are orthopara directing. They are orthopara directing, right? But the interesting thing is, they are also deactivating groups. Remember these things actually orthopara directing, and benzene activating groups. Okay, because these are halogens, no, so they can pull the electrons from the benzene ring again. That's why they have given, even though they are orthopara directing, they are deactivating groups. Anyhow, the meta directing groups are deactivating groups. So therefore, the ability of electrophilic substitution increases for this direction. Students, tell me which compound can do the electrophilic substitution more, right? Which one has the highest capability of doing the electrophilic substitution? Aniline, right? Aniline, right? The electrophilic substitution ability in aniline is greater than, now here we have phenol, second one is phenol, right? Then third one is OCH3, like this. Can you understand? Right? So here we can see that the less one is nitrobenzene, then cyanobenzene, likewise. Can you understand? Quickly note down this one. So is there any possibility to conduct the past paper class after 12:30 on Saturdays? 12:30 won't be to do that one, because actually my Saturday 2 classes are there, 4 to 7. Physical class is there in Master Academy, and then 8 to 11 your theory class is there. Before 4 I'm free, but 12:30 to 4 actually 12:30 and කැතයි වගේ නේද නිකන්. ඇද්ද වෙලාවක් අරගෙන දවල් වගේ. So morning is fine, no, right? Get up early in the morning and get ready. It's very difficult for me also. I don't like to get up early. But what to do? You have 7 months remaining. I have to do something for you. Oh, 7 to 12. Okay, let's see what we can do, right? So only for this week, let's start from 7 and let's see what will happen. Because the thing is, if I start 12:30, I have only 3 hours. But if I start 7, so I can take a complete morning time until evening if I need to discuss more questions. Actually, that Saturday morning time is separated for the 26 batch. There are extra classes going to happen there. And your extra class is actually normally in Tuesday. Sometimes we are conducting, sometimes we are not. So for them also, Saturday morning is their extra session time. So let's see, okay? I'll let you know. Anyhow, don't worry, I'm providing the recording. No issue. The reason that I started this past paper class is actually 26 batch students also, some of the students requested me. So why don't we do past papers in the theory class? But in the theory class, we can't do the past paper students. So we don't have enough time. So let's take separate time and let's do the past of this. Before your exam, if we can finish all the past papers, it's really good, Nick. Let's try. Let's try our maximum. Saturday at 9 a.m. Tarun sir's class. Okay. If you have Tarun sir's class, then don't attend for my class because he has already put that class name. So then I'll limit that one for only for the 26 batch. For you all, what we can do. So you can only watch the recordings. Huh? That's what you can do. Sarina. If someone is going for Tarun class, Tarun physics class, don't attend for my session. Don't come to my class. You go for Tarun class and you can watch the recording. Okay. Because he has already taken that time. No, sorry, now don't do that. Don't do that. No need to rearrange that one. You attend for the Tarun class. Okay. And you can watch my class recording. Okay. Right. Okay. 10. Now look at this one. Now let's do a small exercise on orthopara directing ability. Exercise number 1. Chlorine, and here we are adding anhydrous ferric chloride, FeCl3. Then chlorobenzene is produced. Now students, look at this one. CH3C double bond Cl and anhydrous aluminium trichloride, AlCl3. So this is actually Fiedler-Crafts acylation. Okay? So this is Fiedler-Crafts acylation. Now tell me what are the possible products. Now you know that orthopara directing ability and beta directing ability. Tell me chlorobenzene. Is it orthopara directing ability or beta directing ability? What is it? Chlorine doesn't have any double bonds or triple bonds. So therefore we can say that what? This is orthopara directing ability. Therefore I can say that the products that we can obtain is, we know that in the Fiedler-Crafts acylation, electrophile is C double bond or CH2. Then it is connected to the ortho position. But remember, there is another product. There is another product where it is connecting to the para position as well. Both are possible, ne? Dekama hari. Both are correct. Can you understand? So what about if I connect the C double bond or CH to the other side? Other ortho position? No, students, both are same, right? Under the discussion of benzene, we discussed that one. Both are same, right? So therefore, this is the ortho product and this is the para product. In the conversions, you can use the relevant product that you need to do that, to continue that conversion. ඔයාට අවශ්‍ය කෙනාව තෝරගෙන you can do the conversion, right? Next one, number 2. CH3C double bond O Cl, anhydrous aluminium trichloride. Then what is the product? Friedel-Crafts acylation, C double bond O CH3. Right. So let me connect that one here. Then now I'm going to add chlorine and anhydrous ferric chloride. What will happen? So you can see that this is actually, this is what? Meta directing group. Meta double bond is there. Then you can connect the chlorine atom for the meta position of the benzene ring. Here in this way. Can you understand? So this is the product. This is the only product we can have. So likewise, ortho-para directing ability and the meta directing ability are affecting for the products that we obtain in a organic reaction conversion. Right? So that's why we discuss that ortho-para directing ability and the meta directing ability. Right? Now let's do a conversion like this. Benzene, this is converted into in this way. Not more than in 4 steps. Not more than in 4 steps. How do you do this conversion? Quickly do this one. How do you obtain this product? Not more than in 4 steps. If you have completed third one, do the fourth one. So the fourth one is not more than in 4 steps. Raise your hand those who completed third one. Okay, Supipi, very good. Very good. Yes. So we can start this one with the Fiedlercraft acylation. Right? And we know that this is meta-directing group, right? So since it is a meta-directing group, I can add Br2 FeBr3. Br2 anhydrous FeBr3. Then the product is this way. Then for this one, we can add CH3MgBr, H3O plus. And here, PCl5. Right? So PP is this way that you got the answer. Okay, very good. Friends, in the third one and the fourth one, small difference is there, right? This bromine atom is connected to the para portion, right? Just think about it. Small difference is there. If you want, you can do that one in the final step. Ne? But BR at first. Yeah, you can start with BR also. Because adding BR is also, bromobenzene is orthopara-directing group. We can do in that way, doesn't matter. But I'm going to do in a different way. I'm starting from the same compound, same this. Right? I'm going to start from the Fiedlercraft acylation. Raise your hand those who completed the fourth one. Raise your hand those who completed the fourth one. Okay, so pretty good. Let me start from the same Friedel-Crafts acylation. Then here we can add Grignard region, CH3 MgBr, secondly H3O plus. Then we have OH. PCl5, Br2 FeBr anhydrous. Number 5. Do the fifth one in this way. Here we have the benzene ring. Two deuterium atoms are there. Not more than in 4 steps. Anyone completed the number 5? Done. Good, very good. Raise your hand those who completed number 5. Okay, Asma and Sukriti, very good. Right. Now look at this only. Look. First of all, I'm going to add chlorine, anhydrous ferric chloride, then producing chlorobenzene. Chlorine, anhydrous ferric chloride. And we have two chlorines in this, right? Because this is a orthopara directing group, I want to connect the two deuterium atoms in this way. So therefore, I take the decision to connect that chlorine atom in the para position. Nothing wrong with that one, right? So no point of connecting that chlorine to the ortho position. You can connect there, but no point, right? Because I want to have the product like this. Then I can add magnesium brighter. Then I have a green art region like this, MgCl, and here also MgCl. Then D2O is added in this way. So the conversion is like this. I'll give you two questions as a homework. Do that one as a homework. Huh? Two questions as a homework. Question number 6 and 7, do them as a homework. Question number 6. We are starting from the benzene ring. Not more than in 5 steps. Not more than in 5 steps. Number 7, we are starting from chlorobenzene. Not more than in 6 steps. Right? So do these two as a homework. Right, okay? Are we done? Right. Okay. Okay, students. Then these are the things that we have to discuss today. What are the doubts you have? Anything? Any doubts that you want to ask? So today we discuss about small revision, recap of aldol condensation reactions. Then we discuss about halogenation of benzene and some reactions. Then we discuss about orthopara directing ability and meta directing ability. And we did some example reactions, conversions, right? So now you have to do these two conversions as a homework. Now still time is 10:50. Okay. So you can wake up until 11, 11:30, 12, and you can complete these two conversions and send me the answers. Let's see those who have just that much of courage to woman are, right? Do these two conversions and send me. Right. Okay. So next we are going to meet in the Friday paper class. As usual, we will conduct in the paper class. We have to discuss an essay paper, right? So we have to discuss essay paper. We have to start next paper book also as soon as possible. Chemical kinetics also there. Organic conversion should be included there. So a lot of things to do there. Okay, right. So, right. Raise your hand those who understood the things that we discussed today. Quickly raise your hand those who understood the things that we discussed today. Good. Right. Okay, then let's meet on the Friday paper class. Until then, bye bye. Have fun. Good night for all of you. God bless you.